Oh, I have people now. There are 2 of you. Ask me questions. If you hear clicking, it's dogs clicking. If you hear barking, it's dogs barking. Benzene's connected to the cyclohexane. The cyclohexane's connected to the cyclopentane. The cyclopentane's connected to the cyclohexane again. These are the parts of the molecule. Ah. And here I wait. Lindlar's catalyst versus palladium and carbon. Lindlar's catalyst it's a poison catalyst, so instead of going from a triple bond to a single bond, you can only go to the double bond. So it'll give you an alkene instead of an alkane. If you just did regular palladium on carbon, it would take and hydrogenate every single double bond, every alkene and alkane, or I'm sorry, alkene and alkyne. That won't happen with Lindlar's catalyst. It stops halfway. Let's see. So, oh goodness, let me try that again. Wrong arrow. So we have 2 options here. Well, really 3 options, because we also have the ammonium and lithium. Sorry, just a second. So if I just did the palladium on carbon, I would get ethane. And then trying to see. Yeah. So there is, and I don't want to play any volume.
In this video, we're going to talk about the reduction of...
Just seeing if there was a video for that. So if you go to, I'll paste it in the comment box. That video there, that might be faster than me trying to draw it all out, but that video will show you Lindlar's catalyst and lithium and ammonia, or sodium solid and ammonia. And you can look at how those will give you the either trans stereochemistry or the cis stereochemistry, depending. And then the palladium on carbon just reduces everything so that you don't end up with a double bond when you're done. Hope that makes sense. Next question. I'm just still working on this since no other questions came through. I gave a bad example because there's not going to be any. Thionyl chloride and tosylate groups, or tosyl groups. Well, thionyl chloride is when you want to convert an alcohol to a halogen, and a tosyl group is when you want to make an alcohol good leaving group. So you use them in different contexts. Are those the only questions? I can sit here and just keep playing on my computer and you can stare at me doing it. You can tell Jason no. I said that there are tables of like solvents and stuff you can know. to tell you whether or not something's going to be favored for a substitution or an elimination, but for the sake of our class, I'm going to do, I'll just let you know which reaction I want you to show. Now, I do expect you to know whether something will do an E1 versus an E2 or an SN1 versus an N2. And for us, we made the assumption that all tertiary carbons will do the unimolecular, and then methyl primary and secondary will all do the bimolecular mechanisms. Retrosynthesis. A retrosynthesis is any time you have something and you go backwards. So you would start off with this, and let's see. Let's pick, where are my other elements? There we go. Oh, for the love of goodness. And try that again. I'm on the struggle bus today. Hold on. Okay. So let's say I wanted to make a molecule that has a bromine on it. I could say, what would be one way that you could make this? What would be a way to make this where you would start off with an alcohol, for example? Normally a retrosynthesis for a teaching course, I would have to tell you what type of starting material I wanted you to start with, because otherwise you would have no idea what types of reactions to even try, because at some point you could have lots and lots of different options. So if I said what, and I don't know if there is a synthetic or a retrosynthetic arrow in ChemSketch. I'm not seeing it. That doesn't mean there's not one here, but oh, there we go. Okay, hold on a second. I can make that work. The retrosynthetic arrow has a different look to it. I want it. I'm subscribed to your channel and got a notification, but I'm pretty sure this is for you. Yes, this is for organic too. I only have one channel for all my classes, Amanda. Oh, there we go. Aha! Figured it out. Okay. So you have your retrosynthetic arrow. That's what this would look like. I don't know why it's kind of funky looking. Okay, that fixed it. So if I said, what would be a way that you could make this using an alcohol? Okay, so hopefully you would look at that and start with cyclohexanol. But there would be actually a couple different ways to do that. So if I wanted to start off with my cyclohexanol, and let me just put this down here. You know, what would be the options that we could have for that arrow? So I'll just write some of these out. So number one, we could use HBr, right? Where you would take alcohol, you would protonate it with the HBr, and then the bromine would come in and do a nucleophilic substitution on the good leaving group of the alcohol, okay? Number two, you could use potassium, why did I say potassium? Phosphorus tribromide, PBr3. If you were wanting to change it with a chlorine, you could use the thionyl chloride, the SOCl2. Then a third way, let's see. You could convert the alcohol into a good leaving group using a tosyl group. So tosyl chloride and pyridine is usually what you see them together as. And then after that, you would have to have another step where you would come in and displace that with a bromine ion. Okay. So maybe sodium bromide, something that would have a Br minus that could kick off the tosyl group. So that would be kind of an example of a retrosynthetic reaction, where you would take a product and say, this is how I could get to that product from this starting material. But I would still need to give you the starting material and the product. So does that make sense? One green blink, I have no idea who you are. Yeah, anytime you see that big, like, double-sided arrow, always think retrosynthesis. Always realize that that's your product and you're trying to go to your starting material, or figure out how to get to a starting material and reagents that would give you that product. It's just another one of the, like, 400 arrows that we have to show stuff. Crystal, did Jason want to memorize all of the solvent tables? That's correct. So the E1CB, you get a carbanion because it's adjacent to a beta carbonyl. And so, yes, he did. Tell him I'll give him a bonus point if he memorizes the whole thing. I'm joking, don't do that. Focus on other things. But so the carbanion will be stabilized through resonance with the carbonyl that's attached to it. So if you have, if I show it this way, so I have a carbonyl, and then if I have a carbanion right there, what just happened? Here, it's spent, now I remember. I didn't even give him one. That's just ridiculous. Oh, did he do the one in the book? Why won't this let me get a negative charge? Ah, there we go. Okay, so let's say that this is my carbanion, and then you would have resonance set up between this. And I showed this one on the board, so you probably have something like this in your notes somewhere, where you would get a double bond there, and then the oxygen here. And because you have that kind of stabilization through resonance, it allows this carbanion to be more stable, and so it's able to do this weird E1CB reaction instead of the E1 reaction. I hope that makes sense. I will write resonance stabilized. Remember that any reaction that happens, it is always going to happen in the most thermodynamically stable way. It's always going to make things that are lower in energy than what you started off with, right? We can't make things that are freaky reactive and things like that. So, and the way that we have to do things to make things reactive is by basically making more reactive stuff to make less reactive stuff react, and things like that. You'll see that when we talk about aromatic reactions. But as long as you have some sort of resonance stabilization like we do in the case with the E1CB, it's going to make it able to do things that a regular leaving group alpha to a CH2 group or methylene group would be able to do. It's just going to be a little bit different because it's got that whole extra resonance stabilization aspect. In the meantime, Cam, that's his butt. Hey Red, say hi. Twinkie Cam. Hi Twinkie. I had to show pictures of my dogs. Dogs are ridiculous. They're actually being very well behaved right now, which is unusual for them. I have to broadcast this from my bedroom because otherwise they will fuss and complain at me the whole time I'm on the computer. Where's my... There it is. That's a great question. So we haven't gotten into those details yet this semester, and I wasn't going to until we do some chemistry that does not have like alcohol halide functional groups, like something that has harder functional groups. But we haven't done really anything with priority rules. So the way the priority rules work is that the most reactive functional groups get the highest priority. Now, as organic students, you probably wouldn't know what the most reactive functional groups are yet, unless you memorize the list that I gave some of my students last semester. So it's like carboxylic acid, aldehyde, ketone, alcohol, amine, and it kind of goes down this list. So if you memorize the list, then you know which needs to be the lowest number, which has the highest priority. Anything else gets named as a prefix unless it's part of the parent chain. So if it's an alkene or an alkyne in the parent chain, you still put that with the parent chain name. So hexene, hexine, that kind of thing. My dog just huffed at me. And so then if you have, let's see, what would be first and last? Something multiple groups and triple double bonds. Yeah. So far, because there's a bunch of students in class that haven't had Organic 1 with me, so they didn't learn about the priority groups and things, then we're not going to be covering those just yet. But let's say, for example, I had something, I can still give you guys an example, so. Okay. So let's say I have a molecule with a NH2 group and an OH group. Okay, so how would I name this type of cyclohexane? Well, I would look and I would still know that my parent chain is cyclohexane. And I would look here and say, which has the higher priority? Well, I know, because I know the list, that the alcohol gets first priority, and then an amine would not have the highest priority. So that would mean I would number this carbon number 2, just because they're adjacent, 1 and 2. Then I still have 6 carbons, but there's nothing on 3, 4, 5, and 6, so I don't have to write anything down there. So in the case where you have something with a higher priority than another, then the lower priority gets put as a prefix. So we would have 2-amino, cyclohexane, 1, all. There we go. Now, if it's the case with something that has equivalent priorities, then we go with alphabetical. So the only example that we would do that with, and once again, I'm not going to give something like this on the exam yet because we haven't, why does it keep doing that? Because we haven't covered these in that level of detail. But if we had a molecule, let's say had put fluorine, and then chlorine, and then an iodine. Okay. So if I were to take this, and I just realized it's in Chem Sketch, and I can totally just name this on here. So generate name for structure. So if you look, it's still alphabetized everything. So chloro before fluoro before iodo. It still put cyclopentane as the terminal chain there. It made it so that fluorine was on carbon 1 Why did it put fluorine on carbon 1? We usually go alphabetical for those. Oh, because we would still need them to have the lowest possible number. Okay. Well, what I'll tell you is that you're not being tested on that tomorrow because we haven't gotten there yet with the class. So I gave a really bad example here that doesn't make any sense. So I'm going to erase that because that's got something special on it. But this is essentially what I taught last semester, but we haven't gotten there yet. So I appreciate the question and I'm glad you're thinking about it, but in the meantime, just think about easier nomenclature questions, like things that would have a suffix and a prefix, but things that would always be a suffix or prefix, like an alcohol and a methyl group or something like that. Is that clear? Hopefully. Green blink. Yeah, I won't be giving you anything with a double and triple bond on the molecule on the test. But if you ever want to know, you can always make them up in ChemSketch. Give yourself a question and see if you can figure it out. That's what I do a lot of times if it's something that's kind of particular like that. So let's say I want to know what has a higher priority, an alkyne or an alkene. So let's make a molecule where, depending on how we would number it, you know, you would either have the alkyne at carbon 1 and the alkene at carbon, 1, 2, 3, 4, or vice versa. So you can always go through and check by doing the tools, generate, name for structure, and it'll put whatever has the highest priority on the bottom. So you've probably noticed that with alkenes, we've seen a lot of chemistry that those can do. And that's because they actually do have a higher priority than an alkyne. Alkynes, because they're so close together, they tend not to be particularly reactive. So I'm checking my... Somebody just sent me a text and I don't know who it was. Okay. Yeah, I think it's always interesting to just, you know, draw something and check. But obviously, it depends on all the other functional groups that are on a molecule, because some things take priority over others, so it kind of, you have to consider it in the context of everything else that's on there. I have a dopey dog staring at me right now. What type of trouble are you having with Gilman's reagent? We didn't really learn a mechanism for it. Red, nobody wants to hear that. Okay, I'll go back to drawing. What? Red dog, stop it. Okay, so when you're working with the organometallics, oh, for the love of God, really? You're going to have like 4 people standing there like, hey, is that Dr. Mann? I recognize her voice. Okay, so anytime you're working with the organometallics, realize that you're essentially forming the equivalent of a carbanion, which is, going to be super nucleophilic because it's a carbon with a negative charge and a lone pair on it that wants to attack stuff. So if you have something in there, and I'll just draw it without the metal ions and stuff attached to it. So let's say that middle carbon here is what's going to be our carbanion. So that's the one that originally had a halogen on it. That's the one that originally reacted with the copper and the then it reacted with the lithium and the iodine and all that, right? So let's imagine that's what you have. If I have that in a molecule with anything else, so let's say something that has a good leaving group on it, like chlorine. Okay, so now this is just a basic, essentially nucleophilic substitution reaction. Nucleophile attacks electrophile. So the biggest nucleophile here is going to be the carbanion. And then the electrophile is going to be the carbon that's attached to a halogen, so the partially positive charged carbon. And the reason for that is because that chlorine has a partial negative charge, the carbon has a partial positive charge. That nucleophilic carbanion is going to be attracted to that partially positive charge on the haloalkane, alkyl halide. So essentially what you're looking at then is a reaction where your nucleophile attacks an electrophile, just like anything else that we're doing. And in this case, our nucleophile, this is going to have a leading group and everything, so it'd still follow the same things as a regular nucleophilic substitution reaction would. Where's my... I have a problem here, hold on. It's not wanting to convert that into an arrow for me. Oh, drat. I have a window open somewhere that has all of these on it, and I can't find it now. Anywho, the carbon that's the anion, the carbanion, would attack that carbon and kick off the chlorine, basically forming a carbon-carbon bond, which is why this is such a useful reaction. We don't have a lot of molecules that are going to make carbon-carbon bonds because those are really strong bonds. And because they're really strong bonds, they're hard to make, they're hard to break, etc. So hopefully that makes sense. I'm sorry I can't draw the mechanism arrow. I can't find the... It has like an extra toolbar that pops up for that. I can't find it right now. But that's essentially what Gilman's reagent is facilitating. It's doing it because carbanions are so unstable, it has to be stabilized through the use of those metal ions. And then ED-Jason ion, if you're hydrogenating vegetable oil that has 6 carbon-carbon double bonds, how many equivalents would you need to use? Well, I don't know. What do you think? 6 carbon-carbon double bonds? Let's draw something out that looks like that. 6. Well, let's see. So 1, 2, 3, 4, 5. Okay. Double bonds. 1, 2, 3, 4. Whoops. 5. 6. Okay. So there's a ridiculous molecule that has 6 double bonds, right? So I would need an H2 for this one. I would need one for there. I would need one for there. And there. So I'm going to agree that we would need 6. You get, 1 hydrogen adding to each carbon. You have 2 hydrogens per H2 molecule, so 6. Are you eating like 4,000 carbs right now at Panera? They have that good hot tea though. They've got that blueberry hot tea over there. I like that. I'm running out of room on my little sheet here. Oh, what did I do? I can't be trusted with this apparently. So I assume that you know everything from Organic 1. I don't think we covered inversion enantiomers though. Your book has that? I've never heard of that. I've heard of enantiomers and Google's not pulling anything up. Did you spell that wrong? Oh, yeah. So we were talking about that with the inversion of configurations regarding nucleophilic substitution reactions, so I expect you to know that. And the conformational isomers, and that's pretty straightforward stuff from Organic 1, so I would expect you to know that as well. Red, stop fussing. I doubt you guys can hear it, but he has the most high-pitched whine on the planet. And he uses it whenever he doesn't think you're paying enough attention to him. Which would be right now, apparently. Right, cut it out. Okay, well, if you guys don't have any more questions, I'll be getting off at 7:45. Because I still gotta write an exam. For you. Just for you. Wait! One more. Okay, one more. Bring it on. Yeah? Let's see. Go ahead, cut it out. So... bromotert-butane, Red, stop it, would have 3. Major, minor, mediocre. Right, so if there were 3 asymmetric, so let's say they were all different, right? Oh, shoot. That's not what I wanted. Let's say that I had a molecule that had 3 different groups on it. Like that. You would get a mixture of 3 products. I would never give you anything like that on an exam, though. That would be sadistic. I try not to be that evil. I like that, though. A major, a minor, and a mediocre. I think you mean Zaitsev's rule? Yes. Anytime you have an elimination reaction, I expect you to know which would be a major and a minor product. Same as with Markovnikov rule, I expect you to know what that is and, you know, how that impacts things. Alright. If you were doing it, you would know that you would get multiple products. I'm not sure I know what you're asking me. Zaitsev's rule. Zaitsev's rule says that you make the most substituted double bond. So I expect you to know that the major product is the... Sorry, my dog's nails are clicking everywhere. I expect you to know that the more stable double bond, the one that would be the most substituted, meaning the most carbon groups hanging off of it, that would be the one that you would form. That was a piece of information you were missing then. That would be important to have. So, yeah. If I have a oh, wait. Where is it? Here we go. Carbon-carbon double bond. And I'm just doing this on paint because it's a little bit faster for me to do it this way. So let's say this is a carbon group, and then the rest of these are all hydrogens. Okay? Oh no, make that a CH3 also. And I'll make that a CH3. So this would have been a major product from an elimination reaction, but a minor product could have happened because there was a second alpha carbon there, right? This carbon here would have had the original leaving group on it, and then this CH3 could have been deprotonated, as well as this one here. So it just kind of depends on what you have there to start off with, but yeah, I wouldn't give you one that has 3 products. Make sense? Okay, I'll write a little note here. And with that, I will leave you to study, because I have to write an exam. My handwriting's getting smaller and smaller. I tried. Anyway, bye everyone. I'll see everybody tomorrow. I still have office hours from 10:15 until 11:15 tomorrow. So if you are watching this after the fact and you say, I really wanted to know about something that didn't get asked, that's totally fine. I do come straight in from home at 10:15, so if I'm like 5 minutes late, I'm sorry, it just means I ran into traffic. But you can totally come to my office at 10:15 and ask any last minute questions, okay? Bye everyone. Have a good night studying.